Okay, Introduction to Electric Circuits, Grade 12, Physical Sciences, Part 1 of 5. Okay, electric current is the rate of flow of charge through a circuit. In other words, electric current is a measurement of how many electrons flow through a particular point in a wire. Okay, using the first definition, we have the following formula. The current is equal to the charge over the change in time. Okay, when you have the word rate, you have to understand it is division by change in time. So, the SI unit for current is ampere. This was named after a French physicist and mathematician by the name of André Marie Ampere. Okay, other units for current can be coulomb per second. Coulomb, the unit for charge, and second, the unit for time. Okay, so you have coulomb per second. When you bring second to the numerator, you are going to have an exponent of -1. So this is coulomb per second. So the one we are going to use most of the time will be ampere. Okay, the SI unit for current. Okay, this is the one we are going to use most of the time. Okay, so with this circuit, when you have a closed switch, you have a complete circuit. Okay, so for electrons to flow, voltage is required in order to push electrons through the circuit. Okay, voltage is required in order to push electrons through the circuit. Okay, so for electrons to be pushed through a circuit, voltage is required. So the push or voltage. Okay, the push is the voltage. So the voltage is provided by a battery or energy source. So this is a battery. Okay, and in a battery, chemical energy is converted to electrical energy. Okay, inside a battery, you have some chemistry going on inside the battery. This chemical energy is converted to electrical energy. And in a light bulb, okay, in a light bulb, the electrical energy, now the electrical energy is converted to heat and light energy. Okay, so you have light when the switch is closed and the light bulb is hot. If you get close to the light bulb, you are going to feel that it is hot. Okay, an ammeter. Okay, an ammeter is used to measure current and it is connected in series. Okay, an ammeter is connected in series. Remember, current is a flow. So, for you to measure current, which is a flow, you have to connect the ammeter along the circuit. So, you have to connect it in series so that you can measure the flow, which is the electric current coming in the conductor. This is the right way to connect an ammeter. You connect an ammeter in series, and the other reason why we connect an ammeter in series, it is because an ammeter has got a lower resistance. Okay, and a voltmeter is used to measure voltage. Okay, potential difference or EMF, they are known as voltage. Okay, so a voltmeter is used to measure voltage and it is connected in parallel. Okay, you have to connect a voltmeter in parallel. Okay, for example, if you are required to measure the voltage of this battery, you are going to connect your voltmeter in parallel so that you can measure the voltage of this battery. Okay, so the right way to connect a voltmeter is in parallel. Another reason why we connect a voltmeter in parallel is because the voltmeter has got a higher resistance. Okay, so we carry on. The formula for calculating charge can be derived. Okay, from this formula, we can derive the formula for calculating charge. Okay, we use Q to represent charge. What you can do is to multiply by change in time on both sides. When you multiply by change in time on the right side, you are going to be left with Q, which is the charge. So you do the same on the left. You are going to have the current times the change in time. Okay, let me show you. You multiply by change in time on this side. You also do it on the left side. Okay. Okay, so you're going to cancel this and this. Okay, so what you're going to have is Q, which is the charge on the right side. This is equal to the current times the change in time. Okay, current times the change in time. So this is cancelled. Okay, you can see. So we carry on. Now, the SI unit for charge is Coulomb. This was named after a French physicist and engineer known by the name of Charles Augustin de Coulomb. Okay, the formula for calculating change in time can be derived. Okay, so you can derive the formula for calculating change in time using this or this. Okay, you can use this or this to derive the formula for change in time. So using this, what you can do is to divide by current on both sides. When you divide by current on the right side, you are going to be left with change in time is equal to, when you divide by current on the left side, you are going to have the charge over the current, and the SI unit used is second. Okay, we carry on. Now, Ohm's law. Ohm's law is about the relationship between electric current and voltage. So, the statement says, Ohm's law states that the voltage across a conductor is directly proportional to the current through the conductor provided the resistance of the material remains constant. Another statement of Ohm's law states that the ratio of voltage to current is constant provided other physical factors such as temperature remain unchanged. This is another statement of Ohm's law. So, using this statement, we can come up with this formula. Okay, the voltage is equal to the current times the resistance. Okay, and the SI unit for voltage is volt. We use V to represent the SI unit for voltage. Okay, this is voltage, and we also use V to represent the unit volt. Okay, so if you want to remember the above formula, use the following. Okay, remember voltage. Voltage is a push. Okay, you first push. You are going to have movement. You are going to have a flow. Okay, when you push, you are going to have movement or a flow. Now, along the way, you are going to have opposition. Okay, this is the order. Okay, so a push is voltage. Okay, this is equal to the flow. Okay, the flow of charge, which is the current times resistance. Okay, as the word implies, resistance, which is opposition. Okay, so this can be represented using this drawing. So we carry on. The formula for calculating resistance can be derived. What you have to do is to divide by current on both sides so that you can have resistance alone. So when you divide by current on the right side, you are going to have resistance, which is equal to, you divide by current on the left side, you are going to have the voltage over the current, and the SI unit for resistance is ohm. We use this symbol to represent the units. This was named after a German physicist by the name of Georg Simon Ohm. So the definition of resistance is the opposition to the flow of charge, or the opposition to the current. Okay, or you can say resistance is a measurement of how easily electrons or electricity can flow through a circuit, and all materials have some resistance, but certain materials resist the flow of electric current more or less than other materials do. Okay, and an ohmmeter is used to measure resistance. Okay, remember the units for resistance. Okay, an ohmmeter is used to measure resistance when the circuit is not energized and it is connected in parallel. You make sure the circuit is not energized. The switch must be open. So if the switch is open, no current is flowing from the battery. So this is what we mean the circuit is not energized, meaning no current is flowing. So you have to open the switch. We also have a multimeter. A multimeter is a measuring instrument that can measure multiple electrical properties. A typical multimeter can measure voltage, resistance, and current. The formula for calculating current can be derived. Okay, from this or from this, we can derive the formula for current. So to have current, you can divide by resistance on both sides. When you divide by resistance on the right, you are going to have current is equal to, when you divide by resistance on the left, you are going to have voltage over the resistance, and again the unit is still ampere or ampere. Okay, let's see graphs of Ohm's law. Okay, so you have ohmic conductors. Okay, conductors that obey Ohm's law. So for ohmic conductors, you are going to have this. You can have voltage on the x-axis and current on the y-axis, or you can have current on the x-axis and voltage on the y-axis. depending on what you have on the x-axis and what you have on the y-axis, you are going to have a different slope or gradient. Okay, now for non-ohmic conductors. For non-ohmic conductors, you don't have a straight line. Okay, so for conductors that obey Ohm's law, okay, ohmic conductors, okay, for conductors that obey Ohm's law, the graph is a straight line. This implies that the resistance is constant. Now, for conductors that do not obey Ohm's law, okay, non-ohmic conductors, okay, for conductors that do not obey Ohm's law, the graph is not a straight line. So this implies that the resistance is not constant. Now, let's look at the direction of current. We have what we call conventional current flow and electron flow. So, if you have a circuit as this one, for conventional current flow, the flow is from the positive terminal of the battery, like this, from the positive terminal of the battery all the way to the negative terminal of the battery. So, for conventional current flows from the positive to the negative terminal of the battery. Now, in the case of electron flow, electrons flow from the negative terminal of the battery to the positive terminal of the battery, like this, from the negative terminal of the battery, okay, to the positive terminal of the battery. So, in the case of electron flow, electrons flow from the negative terminal to the positive terminal. So, to remember about electron flow, note that electrons have got negative charge. So, electrons are repelled by the negative terminal of the battery. Remember, electrons have got negative charge. So, they are going to be repelled by the negative terminal of the battery because like charges repel, unlike charges attract. Okay, negative and negative, they repel. So, this is why you have electrons flow from the negative terminal. Okay, they are repelled. So, we are going to use conventional current flow most of the time. Okay, we carry on. Now, the potential difference. The potential difference is the amount of work done or the amount of energy transferred per coulomb of charge. Okay, so from this definition, you have the potential difference is equal to the amount of work done per coulomb of charge. Okay, Q for charge. So now the SI unit for potential difference is volt. Okay, and other units for potential difference, from this you have the joule per coulomb. Okay, the unit for work done or energy transferred is the joule per coulomb, the unit for charge. Okay, so this will be joule per coulomb. So the SI unit is the one that we are going to use most of the time. Okay, now you have to know that the EMF, which is electromotive force, is the total energy or the total work done. Okay, total. The EMF is the total energy per coulomb of charge that a battery can supply. Okay, the EMF, we use E for the EMF is equal to the total energy, okay, total energy per coulomb of charge. The SI unit for EMF is also volt. Other units for EMF can be the joule per coulomb. So we are going to use the volt most of the time. Okay, so the work done is equal to the energy transferred. Work done is equal to the energy transferred. So sometimes you can have E for energy instead of W for work. You can also have W instead of E. Okay, W for work done. Remember, the work done is equal to the energy transferred. Okay, so when work is done, energy is transferred. So the work done is equal to the energy transferred. So again, both work and energy have the common unit joule. Okay, the unit for work done is the joule, and the unit for energy transferred is also the joule. We carry on now. The term voltage can be used in place of potential difference or EMF. So potential difference is a type of voltage and EMF is another type of voltage. Both EMF and potential difference have the common unit volt. We use V for the unit volt. Let me show you this about the battery. So what you have to know about the battery. This will represent the positive terminal and the short line will represent the negative terminal. Okay, so this is one cell. You have the positive terminal and the negative terminal. Okay, in this case, you have two cells. A cell is a single unit and a battery is a collection of cells. Okay, so we move on. Okay, so a resistor is an electrical component that limits or regulates the flow of electrical current in a circuit. The symbol used for a resistor is this or this, and a rheostat is a resistor with variable resistance. Okay, a rheostat is a resistor that can be adjusted. Okay, and the symbol used for a rheostat is this one or this one. Okay, you have an arrow to show that it is a rheostat. Now, in this picture, you have the types of resistors. Okay, you have the types of resistors. As a grade 12 student, you don't need to know all these types. Maybe you need to know a rheostat, which is a resistor with variable resistance. We carry on. Now, resistors in series and parallel. Okay, in series, for example, okay, as an example, so you have resistors connected one after the other. Okay, R1, R2, R3, R4. This is a connection in series. Okay, now in parallel, you can have, for example, this is a connection in parallel. R1 is in parallel with R2 in parallel with R3. Now, in series, you have to understand that one current is the same for each resistor. Remember current as a flow. Okay, remember current as a flow. So, when current is flowing, the current that goes through this resistor will be the same current that will go through this resistor and so on. Remember, current as a flow. Number 2, voltage divides in series. Okay, voltage divide in series. Voltage is a push. Now, in parallel, you are going to have the opposite of what you have above, okay? You are going to have the opposite of the above, 1 and 2. So, for parallel connection, 1, the current divides for each branch, okay? Not the same, but the opposite. Current divides for each branch. This is one branch. This is another branch. This is another branch. Okay, we don't have to say for each resistor because in one branch you can have more than one resistor. Okay, remember current as a flow. So when current flows, when current meets a junction, the current divides or splits. Part of the current goes this way, another part goes this way, and another part goes this way. Okay, remember current as a flow. Now, 2, you take the opposite. Voltage is the same for each branch, not for each resistor, but for each branch, because on one branch you can have more than one resistor. Now, the formula for calculating total resistance in series and total resistance in parallel. In series, you are going to add R1 plus R2 plus R3 plus R4 and so on, depending on how many resistors you have in series. And for total resistance in parallel, RP, you have 1 over total resistance in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus and so on. Okay, let's move on. So, the EMF is the total energy or the total work done per coulomb of charge that a battery can supply. And the EMF and potential difference are closely related, but they are not the same quantities. Okay, we are going to see that. So, the EMF is the potential difference created when no current is flowing in the external circuit. Okay, so for you to measure the EMF, the switch must be open. So, if you buy a battery, on the battery, you are going to see a voltage indicated on the battery. So, this battery, you have 9 volts indicated. So, this is the EMF of this battery. The EMF of this battery is 9 volts. If you buy, for example, this battery, you are going to see it is indicated that the voltage is 1.5 volts. Okay, you can see 1.5 volt. So this is the EMF. Okay, if you have this battery, the type you use in a car, you are going to see that there is 12 volts indicated on the battery. So this is the EMF of this battery. We carry on. So for you to have the EMF, the switch must be open. Okay? The switch must be open for you to read the EMF. So when the switch is open, now with your voltmeter, let's say the voltmeter reads 3 volts. Okay, 3 volts when the switch is open. So in the example on the left side, the EMF is 3 volts. Okay, when the switch is open. Okay, when the switch is closed, the voltage reading drops. Okay, when the switch is closed, the voltage reading drops. Okay, so if you connect a voltmeter, you can have, for example, 2.6 volts. There is a drop in the reading of the voltmeter. Okay, so this voltage drop is due to the internal resistance of the battery. So inside the battery, there is an internal resistance due to the component inside the battery, due to the chemistry going on in the battery. So the voltage reading after the switch is closed is the potential difference of the external circuit. Okay, so the potential difference of the external circuit is known as external voltage or the terminal voltage or the load voltage. You can think of this way. External meaning outside, outside of the battery. External or terminal meaning your terminal point. Your initial point is inside the battery and your terminal point is outside the battery. Or load voltage. What is loaded to this battery? Okay, what is loaded to this battery? Or what is connected to this battery? Okay, so different terms can be used for the potential difference of the external circuit. We carry on. In the example on the left side, the external voltage is 2.6 volts. So the voltage dropped by 0.4 volts. Okay, from 3 volts to 2.6 volts. This is known as the lost voltage or the internal voltage inside the battery. The lost voltage or internal voltage is due to the internal resistance of the battery. So the formula for the EMF is equal to the external voltage plus the lost voltage or internal voltage. Internal voltage. The EMF is equal to, remember, the voltage is equal to the current times the resistance. Remember from the previous slide, you have the push is equal to the flow times opposition. Okay, so V is equal to I times R, current times resistance, plus now the lost voltage or internal voltage. This is inside the battery. You are going to have the same current times resistance. This is going to be internal resistance. The EMF is equal to, you have current is common in both. You are going to take it outside of the bracket. Now, in bracket, capital letter R plus lowercase r. So, in the example on the left side, the EMF is equal to external voltage plus internal voltage. This is equal to external voltage is 2.6 volts plus internal voltage, which is 0.4 volts. You are going to have 3 volts, okay, which is the EMF. Okay, energy dissipated in resistors. Okay, energy is dissipated in resistors as heat and light energy. To get the formula for energy dissipated, how can you get the formula for energy dissipated? We know from the previous slide that the voltage is equal to the work done over the charge. And remember, work done is equal to the energy transferred. W is equal to E. Okay, so you can rewrite this as, instead of W, you're going to have E for energy transferred over the charge. Now from this, the energy transferred is equal to the voltage times the charge. Okay, how can you get this? What you can do is to multiply by Q on both sides. On both sides, you multiply by Q so that you can cancel. You're going to cancel this and this. So on the right side, you are left with E equal to, on the left side, you have the voltage times the charge. Okay, we carry on. Now, remember the following formulae from the previous slides. We are going to use these formulae from the previous slides. Now, with this formula, if you can substitute Q, the charge, into this formula, okay, the charge is equal to the current times change in time. Okay, if you can substitute this into this formula, you are going to have the energy transferred is equal to, you have V times current times change in time. Okay, you substitute Q with current times change in time. So you are going to have V times this. Okay, so you have this formula. When you substitute this in place of Q, okay, and now with this formula, if you can substitute V using this formula, V is equal to I times R. Okay, so using this formula, you are going to have this formula. Energy is equal to, you have current times resistance times current times change in time. You are going to have current squared times resistance times change in time. Okay, you have this formula. Okay, let me explain. So you have energy is equal to, instead of voltage, you have current times resistance times current times change in time. Okay, instead of voltage, you have current times resistance, and then times current again, you have current. Okay, times change in time. Now, can you see? You have current times current. You are going to have current squared times resistance, okay, times change in time. So you have this. Okay, let's carry on. Now, using this formula, okay, if you can substitute this formula into this formula in the place of current, you are going to have the following formula. Energy is equal to, you are going to have voltage squared over resistance times change in time. So you have this formula. Okay, let me explain. So you have energy is equal to the voltage. Now, in place of current, you have voltage over resistance. okay, times change in time. Now, can you see voltage times voltage? You have voltage squared, okay, over resistance times change in time, okay. We carry on. Now we have this formula and this formula and this formula for energy dissipated in resistors, okay. Now, electricity in our homes is sold using the following units, okay, kilowatt hour. The kilowatt hour is the commercial unit of electrical energy, okay. We are going to see about the cost of electricity, okay. Now, about power and brightness of light bulb. The power is the rate at which work is done or energy is transferred. Whenever they say rate, you have to know that it is division by change in time. Okay? And remember, the work done is equal to the energy transferred. So work done is equal to the energy transferred. Now, using this definition, the power is equal to the work done over the change in time, okay? Because you have the word rate, okay? The change in time, or the power is equal to energy transferred over change in time. The SI unit for power is watts, okay? We use W. This was named after a Scottish inventor and mechanical engineer by the name of James Watt. And other units for power can be joule per second. Okay, remember the unit for work done or energy transferred is joule, and the unit for time is second. You can write like this. Okay, joule per second. So this is the one we are going to use most of the time. Okay, mostly used. Now, another formula for power. We have this formula. The power is equal to the current times the voltage. To remember this formula, use PIV. PIV. Now, we are going to use some of the formulae from the previous slides to derive some formulae of power. Okay, so using this formula, voltage is equal to the current times resistance. Okay, in the place of voltage, you can substitute current times resistance. You are going to have the power is equal to current squared times resistance. Let me explain. So the power is equal to current times voltage. Now you substitute current times resistance. Okay. Now you have the current squared times resistance. Okay. We carry on. You can also use this formula from the previous slide. You are going to have the following formula. Okay. Let me explain. You have the power is equal to current. In the place of current, you have voltage over resistance. Okay, in the place of current, you have voltage over resistance. You carry on times voltage. Okay, you have voltage. Now, you have voltage times voltage. You are going to have voltage squared over resistance. Can you see? Okay. So with substitution, you can derive other formulae of power. Okay. Now about the brightness. The brightness of a light bulb is determined by the power. As the power increases, the brightness increases. Okay. You have to know that the above, applies to incandescent bulbs only. Example of an incandescent bulb. This one, the one with filament wire. Okay, this is an incandescent bulb. So an incandescent bulb is a type of bulb with filament wire. Okay, we are going to see how to use power to determine the brightness of light bulbs. This is the introduction. Okay, we are done.